So here is this DIKW pipeline in more detail for physics. The raw data is what you produce when the protons collide. It's a collection of sensor measurements, because that big experiment we saw for Atlas is just a whole bunch of sensors measuring what the signals of charged particles in the detection devices, or the energy decomposed in a so-called calorimeter, or the light given out in a Cherenkov counter. And these all are signatures of particles which, when put all together and joined up, give you information on what's going on. Tells you the type of particle, possibly the momentum of the particle, and some indications to whether it's a so-called strongly interacting or weakly interacting particle. So after this raw data, we might get data, which is the next step, which is cleaning up the data with calibration to get the best possible measured values. The event is still a collection of measurements. Now we get to information. Information is, in this case, what happens when the protons collide, represented as a set of final state particles, which are the ones measured in the apparatus. They all have energy values, momentum values, some measure of the charge, and possibly a measure of the type of the particle. This is a baryon, meson, lepton, or photon. So we've now actually transferred to a totally different random variable. It's still a collection of components, but now these components are pretty different. And also the length of the vector, or the size of the collection, has changed, because the number of particles is much less than the number of measurements. Then finally, we get to knowledge, which is what you get when we study the Higgs. We take the list of particles, apply various selections, and calculate properties which are presented in terms of those histograms and scatter plots. So DIKW is you can see, when applied to event data, it just takes events and converts one event to another event. These events get more refined until they get sufficiently refined that we can draw some wisdom from it, such as in this case, the standard model of particle physics is at least in this particular prediction, confirmed. Here in a little bit more technical detail is what happens for this DIKW pipeline for Atlas. Some numbers, namely, here I told you each event was pretty large, 25 megabytes per event. And actually this apparatus sees a petabyte of data per second. That's petabyte per second. And to reduce that petabyte, we use a trigger. A trigger is just means that we select events. And that selection has three levels. The first level is electronics in the detector, so that's detailed hardware. And the second two levels are just software. You run this data through clusters of computers, trying to make a decision whether to keep that data or not, because you cannot afford to write all the data out. So we reduce the basic hardware trigger, gives us 100,000 events per second. And then after the final software trigger, we get a few hundred events per second. Even that is 100 megabytes of disk space per second and a petabyte per year. That petabyte per year is just the raw data. We would have additional data because we need this. We keep the transformation of this raw data. And we also would run so-called Monte Carlo data, which is the test data to try to understand the apparatus. So here's what I said already. The information corresponds to taking the raw data, running it through so-called reconstruction programs that take the raw signals and interpret them in terms of physics objects such as photons, leptons, mesons, baryons, collections thereof. And it's all, of course, done using this global collection of computing, which is called a grid, and has 200,000 cores in it. And then we finally mentioned this knowledge, which is as before, individual physicists making decisions, looking at the data and trying to interpret it. Here is a picture of what happens. We have protons coming from the left and the right, and they collide in the middle here. Most of the stuff actually goes back along the direction of the protons, but some of it comes out transversely, and that's what we trigger on, because that's a signal of an interesting event. Because if you produce a high mass particle, which is what we're looking at, the Higgs, remember, is 126 GeV, and that's compares with a proton of 0.98 GeV, so it's over two orders of magnitude larger in mass. Large mass things produced in these collisions tend to spray out sideways, whereas the typical thing that's going on is all to do with low mass particles, and they just continue up and down the same direction of the protons. This thing at the top left is looking at the same picture, rotated through 90 degrees. Now the protons are up vertical to the picture, and then you can see here 3 transversely produced jets, and that's what's the signature of something interesting going on. Here's just another event with 2 photons. Protons are here along the center here. We have the 2 photons going out transversely. We have these yellow things are the charged particles. You see they're actually not straight. That's because they're bending in a magnetic field. And this comes from another experiment, the CMS experiment. I remember there 2 big experiments, CMS and Atlas. And this is a typical event corresponding to a Higgs particle. And as it says here, the signature of an extreme event or an interesting event is lots of things happening transverse to the direction of the protons. This picture here tells us that really the cross sections are small. This is just a plot of the cross section. This thing here is around 40 millibars, the inelastic cross section. And then we go down here to microbarns, that's a factor of 1,000. Nanobarns, another factor of 1,000, 10 to the 6. Picobarns, 10 to the 9th. Femtobarns, 10 to the 12th. So there's a factor of 10 to the 12th between here and here. And we have Higgs sitting here as a cross section. So the Higgs cross section's down by about a factor of 10 to the 12th from the total cross section, which just emphasizes how rare the production of Higgs is. And this is just a picture of a Higgs being produced here, and then it decays. In this case here is the so-called 4-lepton decay, which is just one of the signatures. Remember, you had 2 photons and 4 leptons as the signatures. Up here we just have another typical picture of an event.